Welcome back. In this segment, we're going to study a counterexample of a big O relationship. In particular, we're going to illustrate one way to prove that a big O relationship does not hold. So for our example, we're going to use the same function f of x that we used in previous segments. So f of x is equal to 999 times x squared. Recall that we proved this function is big O of x squared and big O of x cubed and so on. In this segment, we're going to prove it is not big O of x. Let's assume it were big O of x. What that would mean is that when x is large enough, then this function would be upper bounded by a constant times x. Well, intuitively, that's not possible because when x gets large enough, x squared gets much larger, much faster than x. So even if you take a huge constant in front of the x here, x squared is eventually always going to overcome that constant times x. But that's just an intuition. Let's prove this theorem. In particular, we're going to use a proof technique we talked about and you should be familiar with, is the proof by contradiction. Remember, with this proof technique, we're going to assume the negation of what we're trying to prove. So the negation of this statement is that f of x is big O of x. So let's assume that. And to conclude the proof now, we must be able to infer a contradiction from this assumption alone. So let's get started. If f of x is big O of x, we can apply the definition of the big O relationship to infer that there must exist at least one pair of witnesses, C and K, for which if x is greater than K, then f of x is less than or equal to C times x. Now notice right away that I dropped the absolute value function here in the definition. Let's assume for the sake of this proof that all the values involved, including the values of x and the values of c and k, are all strictly positive, which again makes sense for us in this course since x will be the size of the input to the algorithm, so it makes sense for that input to be neither 0 nor negative, so let's assume it's strictly positive, and therefore the constants c and k will also be strictly positive. So keep that in mind as we conclude this proof. Now, since we have an existentially quantified proposition of predicate logic, we can use the rule called existential instantiation to drop this quantifier and replace each occurrence of C by a particular value of the domain for C. Now remember, C and K are integers. In this particular proof, we assume they are positive integers. So we're going to use that rule and replace the constant C here, which could be any integer at this point, by a specific one. Let's call it C1. And similarly, we're going to apply in the same step the same rule of existential instantiation a second time to pick a specific value of k, again a positive integer, let's call it k1, to replace here this variable inside the proposition. So after we applied that existential instantiation rule twice, we can infer the following proposition. If x is greater than, strictly greater than a positive constant k1, then it must be the case that f of x is less than or equal to a specific constant c1 times x. Now before we move on with the proof, let me make one observation. When we went from this proposition to this one, something significant changed. In this first proposition, we had three variables, c, k, and x, all of which range over the set of positive integers as we assumed. When we used the existential instantiation rule twice, we actually replaced the variable c with a specific constant c1 and the variable k with a specific constant k1. So in particular, keep in mind from now on that C1 is a specific constant, a positive integer whose value we don't know, but it's a specific one. And same thing for K1. So remember, we're trying to reach a contradiction, and in this case, it's not clear maybe yet how it's going to come up. So the first thing we can do is we can simplify this inequality. Notice x appears on both sides, and since x is strictly positive by our assumption, we can divide both sides of the inequality by x. In fact, we can divide both sides of the inequality by 999 times x, since that number is positive. So when we do that, we end up with the following proposition. And now the previous observation becomes important, because K1 is a constant and C1 is also a constant, an integer constant. So when you divide C1 by 999, you get some other constant. Maybe not an integer, maybe it's a rational number, but it's still a constant. And maybe now you should have an idea of where the contradiction is going to come from, because we just proved that this statement is true. And what this statement says is that if x is large enough, or rather for every possible value of x that is large enough, it must be the case then that x is less than that constant. Well, that doesn't quite make sense, because you can always make x large enough so that it's both larger than K1 and larger than this constant. So the rest of the proof will exhibit a contradiction by picking a particular value of x, which is going to make this proposition false. Now, this proposition, which we just proved to be true based on the assumption, we're going to give it a name. We're going to call it P. So as I just explained, we're now going to pick a value of x that is going to be larger than both K1 and this constant. There are many possible choices. I'm going to pick x1 to be a specific integer, namely the integer K1 plus C1. Now remember that K1 is a strictly positive integer and C1 is also a strictly positive integer, meaning greater than 0. So what can we infer from that? Well, we can infer that x1 is greater than K1. Now remember, C1 is a positive integer, so when you add a positive integer to K1, you get something that's larger than K1. And similarly, x1, for the same reason, because K1 is positive, x1 is larger than C1. Now notice we want x1 to be greater than this constant, not just C1. But that's pretty easy, because C1 divided by 999 is definitely strictly less than C1. So in conclusion, we prove that if x1 is defined as it is here, x1 must be greater than K1, and x1 must be greater than this constant that appears here in the proposition. So where do we go from here? Well, we're going to try to find a contradiction with this proposition. In fact, we're going to try to prove the negation of this proposition. So now what we need to do is we need to get rid of this x1 and somehow restore the general variable x. And the way we're going to do that is by using existential generalization. Since x1 is a particular value of a particular integer that has this property, that means, according to the rule called existential generalization, there exists at least one x with that property. Well, yeah, that x in particular, the one we use, is x1. But now we're going to forget about the specific value that we chose, and we're going to be able to infer this proposition of predicate logic. So there exists x such that x is both greater than K1 and also greater than this constant. So you can tell already that this will be in contradiction with this proposition, but let's prove it formally. And the way we're going to do that is we're going to transform this proposition into literally the negation of this one. So the first thing to do is to introduce some negation. So let's use the double negation rule twice, to replace this proposition with this one, and similarly replace this proposition with that one. Now, we have the conjunction of a negation, of two negations, so we can use de Morgan's law to infer the following proposition. If you have trouble with this step, think about applying de Morgan's law backwards from here back to here, and you would see that it works just fine. So you should be able to apply it the other way around in this direction as we just did. The next step is simple. We're just going to replace the negation of x strictly greater than this constant by whatever it means, which is in this case x must be less than or equal to that constant. Don't forget the equal sign. So this is what we have after the next step. Now, don't lose track of where we are trying to go. We're trying to establish a contradiction by proving that P here is true as well as not P. So all we have left to do now is to prove that not P is true. And notice this proposition is very close to not P. So what we need to do in particular is we need to change this disjunction into a conditional and this quantifier into a universal quantifier. You can do that in any order. Let's start with the disjunction, and by using the standard logical equivalence that says that not P or Q is equivalent to P implies Q, we can infer the following proposition. And now you notice that this part of the proposition is identical to that one. Now, as promised, we're going to get rid of this existential quantifier by moving the negation outward across this quantifier. And don't forget, the logical equivalence says, the De Morgan's law for quantifier says we have to switch the existential quantifier to a universal quantifier. So when we do that, we get the following proposition, which, as you notice, is exactly the negation of this proposition, which we call P. So in other words, this proposition is nothing but the negation of P, not P. So now we can wrap up the proof. We prove that P is true over here. We prove that not P is also true. Therefore, we prove the conjunction P and not P, which we know is a contradiction. So now we can wrap up our proof by contradiction, since by assuming this single fact, we were able to derive a contradiction. It must be the case that the negation of this fact is true. And the negation of this fact is that fx is not big O of x. And therefore, this concludes our proof. So make sure you study not just the details, the mathematical details of this proof, but also the big picture strategy of the proof by contradiction to prove that a particular function f of x is not big O of some other function g of x.